engineers, and leaders. In current practice of seismic design, structural safety is the key focus. But what about post-earthquake recovery? And in current design approaches, resilience is not well addressed, leaving questions about non-structural damage, repair costs, and recovery time unanswered. This webinar will present a quantitative assessment of tall buildings performance, covering structural and non-structural damage, repair time and cost estimation, and improving post-earthquake functionality. Our speaker, or distinguished speaker, may I say, is the Executive Director of AITS Solution, Mr. Tong Tot Ong, and the coordinator of our Civil and Structural Engineering Unit, Mr. Shabir Alitalpour. I would just like to inform everyone that for the question and answer, the format will be via Zoom in our chat box. You can write your answers or type your answers as early as you can if you find it more relevant. So let us now hear from our speakers, Mr. Tong Tot Ong and Mr. Shabir Alitalpour, who will share insights on resilience-based design addressing non-structural damage and post-earthquake recovery.
Hello, everyone. Today, we will present the design process of resilience-based design, which consider the non-structural damage and the recovery of the functionality of the buildings. First, let me start with the definition of resilience. Resilience means ability to withstand, and we can recover to the normal condition in a shorter time. So when we consider the resilience in our structural design, it is not only the safety of the building. We have to consider how fast our buildings can be reused in the shorter time span. So in the resilience-based design, the time is also an important factor in our assessment. In the current seismic design approaches, we consider the public safety. It is a primary consideration. When we design the buildings, for normal buildings, we design the buildings to remain elastic or very little damage under frequent earthquakes. But under extreme earthquake, the buildings should not collapse. And we design those buildings to have low probability of collapse under extreme earthquakes. So our primary concern is mainly on the safety. But we do not consider the recovery of the functionality of the building. It is not well addressed. All of you know 2 weeks ago, there was an earthquake in Myanmar, magnitude 7.7 earthquake, which is very strong and very severe damage and casualties in Myanmar. I am from Myanmar. That earthquake also affected the tall buildings in Bangkok. Because of the soft soil basin effect, although the epicenter is about 1,000 kilometers far from Bangkok, we also felt the ground shaking, especially people who stay in tall buildings. Due to that ground shaking in Bangkok, most of the buildings, in the tall buildings, the damages are structural, not the structural damage, non-structural damage. Very few structural damage in a few buildings. So we can say that most of the buildings are safe. But due to the non-structural damage, major damages are in the partition walls, brick walls, and also damage in the ceiling fall down, and some buildings, elevators are stopped. So these kinds of damages affects the reoccupancy of the residents. Fortunately, in my building, there are non-structural damage, partition walls, ceiling damage, but the electricity system, plumbing system, water supply, still they are functional. It is good for me to reoccupy the buildings. But in some buildings, if they have issue with the electricity or water or the lift, in that case, it is some of the residents cannot reoccupy. So that recovery of the functionality is also important, although the building is structurally safe. And also in the current performance-based seismic design approach, we consider we check the structural performance of the building explicitly for the different levels of earthquakes, like frequent earthquake with the 43-year return period, maximum considered earthquake with 2,475-year return period for different structural performance levels. But the post-earthquake functionality is not well addressed. We check the collapse prevention performance level under extreme earthquakes using the nonlinear response history analysis, but still damage in the non-structural components, repair time, costs, and casualties are not analyzed. So in resilience-based design, we have to evaluate the recovery time and also the repair cost. So based on that assessment, we can quantify the risk in more detailed manner, and also we can make the well-informed risk decisions from the different parties, developers, architects, structural consultants, MEP consultants. So all the stakeholders can make the decisions based on that information, considering the uncertainty and downtime and also the financial losses. So in this presentation, we will present the process based on the FEMA P58 guidelines. So we are focusing on the performance resilience-based assessment of the individual building. So when we do the seismic design, first we have to define the seismic input. If we do performance-based seismic design, we conduct the site-specific probabilistic seismic hazard assessment by the PSHA consultant, and they provide us the service level earthquake response spectrum information, maximum considered earthquake response spectrum, and ground motions. So normally for the performance-based seismic design, we conduct the initial elastic design using the wind loading and service level earthquake loading. So in this design stage, we consider the design to be remain elastic. So under ultimate wind and service level earthquake, the building will respond essentially elastic. So when we, in response spectrum analysis, we do not reduce the seismic forces by response modification coefficients R factor. We just use the scale factor 9.81 if we use SI unit in response spectrum analysis and conduct the elastic design. After that, we will get the reinforcement information for the structural components in the lateral load resisting system. For example, vertical reinforcement in the shear walls, longitudinal reinforcement in the beams, coupling beams, and so on. So using that initial reinforcement, we calculate the capacity of the members. For the beams, we calculate the bending moment capacity. For the shear walls, also we calculate the PMM capacity and so on. And we define the actions of the structural components based on their ductility. For example, if the component has the ductile response, like the flexure response of the coupling beams, in that case, we consider as deformation control actions. For the brittle responses, we consider as the force control actions. And then we create the nonlinear verification finite element model for collapse prevention assessment. So using that reinforcement information, we calculate the moment capacity of the beams, and we assign the nonlinear moment hinges in the beams. And also for the shear walls, columns, we can use the nonlinear fiber models, considering the vertical reinforcement information. Then we carry out the nonlinear time history analysis using 11 ground motions and check the responses. For deformation control actions, we check the deformation like rotations or axial strains in the members. But for force control actions, we check the force demand, like shear force demand in the shear walls, and compare with the capacity. If we need to improve the capacity, we increase the reinforcement or changing the member sizes. If it is satisfied, we can say that, okay, we have achieve the collapse prevention performance level using the performance-based seismic design approach. But we do not check the performance of non-structural components after the earthquake, because in collapse prevention assessment, we allow the damage, but the building should not collapse under the earthquake. So the building may not be repairable. But in resilience-based design approach, after we carry out the nonlinear time history analysis, for example, we want to check for the MCE level earthquake assessment. In that case, we have to run 11 ground motions, and then we estimate the quantity of structural and non-structural components that we want to evaluate. So in this step, we have to discuss with the other consultants, MEB consultants, architects, to achieve the quantity of the non-structural components. Then we have to generate the simulated demand sets. We call it a realization. Normally, we generate around 200 demand sets. The thing is, to reduce the uncertainty in the analysis results, we need more data to check to verify the results performance. So 11 ground motions results that we use in PBD is not enough. Normally, we use average of 11 ground motions, but if we want to go further, we need more analysis results. But it is difficult to run 200 ground motions to assess the non-structural components. So what we do is we generate the simulated results based on the Monte Carlo simulation using 11 ground motions results. We create the results in mathematical forms, probably using the Monte Carlo simulation. Then we have to get the fragility curves of the non-structural components as well as the structural components. Those fragility curves are based on the laboratory test results. Then we compute the damage extent of each realization, each ground motion result. Then we compute the repair cost and repair time for each analysis result. So in the assessment, there are mainly three types. The first one is intensity-based assessment. So in that assessment, we evaluate the performance of selected response spectrum. For example, you want to check the design earthquake response spectrum assessment for the resilience-based assessment, checking the non-structural components damage or structural components damage. So you just use that design earthquake response spectrum as a seismic input and assess the performance. Second one is scenario based. That one is based on the user selected earthquake earthquake magnitude and distance. It is like a probabilistic seismic hazard assessment input. So it will consider the uncertainty and intensity of earthquakes around the site. For example, there are 3-4 active faults near the site. So in that case, you can consider all the possible scenarios from those faults. The last one is the time-based assessment, which is most computationally extensive. This assessment consider all possible earthquakes and all probability of occurrence based on the based on the time that you want to consider. For example, the building, you want to check the performance or assessment of the building for 50 years from now. So the building life is 50 years. So within that 50 year, what are the possible earthquakes, all the possible earthquake scenario with different intensity, probability of occurrence, all are considered. It will consider 43-year return period, 500-year return period, and so on. So all possible scenarios are considered in the time-based assessment. So this is just for an example. When we assess the resilience-based design, we have to consider the structural components, beams, shear walls, columns, slabs. For non-structural components, partition walls, ceilings, piping, HVAC system, fire sprinkler system, and also it can also consider the casualties. But here I will not focus on the casualties. I will focus on the structural and non-structural components. So when we do the finite element modeling, if we start with the performance-based assessment, we have to create the elastic models for wind and service level earthquake and check the responses and design the building initial reinforcement using those wind and SLE earthquake domain. Then we create the nonlinear model using the long reinforcement information, and then carry out the time history analysis. So in the modeling, we consider the nonlinear behavior based on the actions. If it is deformation control action like the tactile response, we consider as nonlinear. But brittle failures, we consider as the force control and consider as linear. After that, we analyze the building or 11 ground motions and check the global responses and the local responses. So in terms of non-structural assessment, the global responses like story drifts, accelerations, they are important. So here are the sample results of the building for the transient drift along the height in y direction. So we averaged 11 ground motion results, but this is based on the MCE earthquake. So based on PBD guidelines, the story drift limits are for the average ground motions limit is 3%, individual ground motion limit is 4.5%. So if we satisfy these limits, we can satisfy the global, we can satisfy the collapse prevention performance level in terms of the global responses. But it doesn't guarantee that the non-structural components are damaged or not. And on the right side, the absolute acceleration of the building is plotted along the height. So x-axis is the acceleration in terms of g, and y-axis is the number of story. So when we check the acceleration, there are two types of acceleration. One is absolute acceleration, and another one is relative acceleration. So when we check acceleration, we have to check absolute acceleration. Relative acceleration means the acceleration relative to the ground acceleration. So we do not use that one. Here, these are the local responses for the coupling beams rotation, one coupling beam rotation along the height. They are still within the limit of the collapse prevention performance level, but we cannot assess the damage. So to check the structural and non-structural damages, we have to generate the realization demand sets from that 11 ground motions. So we create 200 simulated demand sets. For example, we have the rotation of our coupling beam at level 22. So we have 11 ground motion stresses. There will be 11 dots here. But using the Monte Carlo simulation, we generate 200 rotation results without running the nonlinear time history analysis. So we plot the rotation results of 200 ground motions. X-axis is the, let's say we assume that it is 200 ground motion. X-axis is the 200 results and Y-axis is the rotation results. So it is in the range of 0.01 radian to 0.03 radian. Same thing, we have to plot for all other components, structural components and non-structural structural components, for example, like shear walls, rotation, or slab column connection rotations, and so on. Then we have to check the damage using the fragility curves. This is one example of the fragility curve for the shear wall. There are other curves for the non-structural components like for example, partition walls, gypsum walls, and so on. So you have to use the corresponding fragility curve for that non-structural component. So fragility curves show the probability of the component based on the damage with respect to the demand parameter. It may be the drift or it may be the acceleration. For example, in this fragility curve for the shear wall, x-axis is the story drift and y-axis is the probability of the damage. There are three types of damage state. The first one is the damage state 1, just a spalling of cover. And damage state 2, it is damage is larger than the first one, exposed longitudinal reinforcing. Damage state 3 is co-concrete damage. So these three plots, these three curves can be obtained from the laboratory test results. Then we have to check the damage assessment of each structural component and non-structural component for each realization. So if we have one partition wall, and then when we check the damage of that partition wall, for example, that partition wall is damage is based on the story drift at level 25. So we have to extract get the story drift at level 25 for 200 results, the realizations. And each realization, we have to check what is the damage level. So we generate the realization realization using the Monte Carlo simulation, and then we do the random number generation using the numbers between 1 to 100 to check the damage state. So from the fragility curve, we will know the probability. Here is a process. For example, for the wall, we have 3 damage states, and the rotation of the wall is 0.01 radian. This wall, wait, I'm showing for the shear wall, but for the partition wall, also same thing. If the story drift is 0.01, story drift ratio is 0.01, in that case, we have to use that story drift ratio. And the realization number is, let's say, 34 out of 200. So for that radian, we have to check the probability. For example, for damage state 1, the green one, the probability is 0.54. Okay. And for damage state 2, the probability is 0.23 at the 0.01 ratio. And damage state 3, it is 0.08. Okay. So occurring of damage state 1 is 0.54 in this table. And occurring of occurring of damage state 2 is 0.23. So not occurring of damage state 1 is 1 minus 0.54. So it will be 0.46. Not occurring of damage state 2 is 1 minus 0.23, 0.77. And not occurring of damage state 3 is 1 minus 0.08. So it will be 0.92. So we can say that if the random number is between 1 to 46, there will be no damage. If the random number is between 47 and 77, we will have damage state 1. Okay, and other damage states are similarly. So we generate the random number. One is between 1 and 100, and compare with these probabilities and decide which damage state will occur for that realization. Here, in this realization number 34, the damage state will be if the damage state, if our random number is 70, in that case, our damage state will be damage state 1. So we have to check all the structural components and non-structural components using that procedure. Then we have to calculate the repair cost. So repair cost also same thing. We have to check for each realization and each damage component. Normally, repair costs are calculated cost per unit of repair in lower bound quantities and upper bound quantities. So it means that if fewer quantities of components are damaged in the realization, so the median repair cost will be high. For example, if we buy the things in the bulk quantity, the price can be reduced. But if we buy few things, the price can be increased. So based on that, the median, we have to decide the repair cost. Then we have to analyze it and check the repair cost of each structural components and non-structural component. This graph is based on the tools that developed for FEMA P58. So we use that tool and plot the repair cost. So here x-axis is the group of the components, and y-axis is the repair cost in US dollar. So here diagonal reinforced concrete coupling beams, it is the repair cost is about 200,000 US dollars, and so on. The non-structural components here in this assessment, the damage is the repair cost is less, but gypsum wall damage is also high in this assessment. And then you can plot the repair cost in terms of realization. For example, x-axis is the number of realization until 200, y-axis is the total repair cost. So the total repair cost for the medium, the 50% of probability of exceedance in this building is about 9.5 million US dollar if we check at the 100 realization. So, and also we can see which group is contributing larger repair cost. But here you can see on the right side, there is a green area realizations with residual drift beyond the limit. If the residual drift, permanent drift of the building in those realizations are beyond the limit, we will not calculate the repair cost. And also we have to calculate the repair time. Normally repair time in FEMA P58 procedure, they consider with the labor factor. For example, labor factor is 80% of the total repair cost. For example, repair cost is $100. Labor factor, labor cost will be $80 for that based on that repair cost. So, and then we have the labor rate. For example, labor rate is $50 per day or something like that. So the total repair cost is let's say $100,000. And then from that $100,000, 80% is the labor cost. In that case, $80,000 will be the labor cost. If we know the labor rate $70 per day, in that case, we can calculate the total number of labor workers. Then we calculate then we estimate how many people can accommodate in that building for during the repair. So we will know then we will know, for example, the 100 laborers can accommodate, then we will divide by the total number. In that case, we can calculate the total repair time for to repair that building. So this is very approximate procedure. If we have the detailed information according to the country, according to the local practice, it will be better. Same thing for the fragility curves. Fragility curves that we can get from the FEMA website, they are based on the US standard and research. So if we have the fragility curve for the brick walls or partition walls or use based on the local practice, it will be good to assess the damage. So here is the repair time assessment. So for this building, the repair time is about 1 year, which is 50% of probability of accidents. So the procedure that I presented is for the individual building assessment. But in future, the trend is we are going to the codes are going to the community resilience, not only the individual building resilience. They will consider the cluster of buildings, city level, and considering the other infrastructure, lifeline systems. So all the things will be considered holistic in holistic approach and check the resiliency. So those procedures are not mentioned in the building codes, but there are manual of practices and guidelines in ASCE. So here are the good MOPs and guidelines if you want to read more details. So that's all for my part. My colleague Shabil will explain you further detail about the time-based assessment, which is the most extensive process.
As Mr. Rong has mentioned in his presentation as well, what we did was that we are now looking at an individual building, and as Mr. Rong described, we are looking at a particular intensity for that building, an MCE level, let's say, for example, earthquake. And we ran 11 ground motion, got the local and the global responses. And after that, we did the Monte Carlo simulation. whereby using the data from the time history analysis, we generated realizations. And realizations are nothing basically but just an MCE event, because yes, this is where Mim Strong was describing for MCE. So that one realization will be an MCE event. And every time we run that realization, we generate some local and global responses based on the input that we have provided from the time history analysis. We calculate the cost it would take to repair that structure. And once we have that cost coming from different components within that structure, we will have one cost for every realization. And let's say if we are running 200 or 1000 realizations, that means that now for those 200 and 1000 realizations, we can actually calculate uh, the probability, because we have realization. Let's say it's the same way that you stand up somewhere and flip a coin, let's say 100 times and 1000 times, and see what is the probability of getting heads or tails, right? This is the same way that we are doing, where we are running these realizations with Monte Carlo simulation to basically get a what we call a median cost. And median cost is nothing but a cost which has a 50% probability of exceedance. And that entire process itself, as Mr. Strong has described, was actually only for one particular intensity. And that's very good process, because if you want to know, let's say, for example, if you're interested, I'm not interested in low level earthquakes, but I'm interested in an MCE level earthquake, what would be my cost, or how much would it take for me to repair my structure? I will have an estimate of it. But if you want to look at the structure's lifespan, then we cannot just rely on a single intensity, because that MCE event may or may not occur, but another event might occur, let's say a service level event, or let's say a design level event, or some earthquake lower or higher than that. Then basically, how do we know how much money are we expected to pay to repair our structure, or how much money are we expected to lose because the structure could be a building which is generating us profits, is not able to operate because we might need to repair the structure or close it down for a while. So in order to evaluate everything for the entire duration of or the entire lifespan of the structure, we then need to run the time-based assessment. And time-based assessment actually is nothing but a multiple. So we run what we did for MCE, we will do the same thing, but for different earthquake levels. So lower, much lower than MCE, maybe different levels. So service level, lower than service level, design level, around sometimes people run about 8 to 10 different intensities of earthquake, and each intensity of earthquake they will then calculate this median repair cost, right? And so unlike a single event, now we are running the same approach for B53 approach, but we are running this approach for now different intensities. And why do we need to run this one for different intensities? The reason why we need to run this for different intensities is that we now actually can combine the information that we are getting from all of those intensities and get what we different parameters, which again will help the owners as well as uh, insurance companies to make financial decisions. And one of the key parameters which actually helps us in making those decisions is what we call the average annual loss. Another key parameter which helps us in making financial decision is what we call the net present value. And so the slide here in front of you actually is again summarizing the time-based assessment process. It's exactly the same process as Mr. Ong has defined in his part, but we just repeat the same process, but for multiple level of intensities, right? And then each level of intensity, now we have, let's say, for example, a median cost associated with the cost which has a 50% probability of exceedance if that event were to occur. Now, if we integrate all of those costs, we will get what we call an average annual loss. So what is that average annual loss? The average annual loss is how much money for example, me, if I am an owner of a building, I'm expected to pay every year if there are earthquakes to occur for next 50 years. Now, how do we calculate that? So imagine that you have a structure whose lifespan is 50 years. every year there can be one or more than one earthquake, but you just note down how much money did you spend that year to repair your structure. And then you average it out for 50 years, you will know what is your average annual cost. So you're averaging the cost that you are paying to repair the structure every year. Now, this information you will be able to from the time-based assessment, because now we are not looking at a single intensity, but we are looking at all but different ranges of intensities that might occur during the lifespan of a structure. Now, then you might ask, well, okay, I know this average annual loss, it's a value, but how do I use it? What do I use it for? Now, the way that you can use it, so before I explain why where you use it, the way that you will calculate this average annual loss is basically you sum up the median loss value, the cost that you are expected to pay for different intensities of earthquake, and multiply that with the annual frequency of occurrence of that intensity of earthquake. And then you sum that value up, you're going to get your average annual loss. So then how do you use that average annual loss? Now imagine that if you are an insurance company and you want to know how much should I charge the owner of the building insurance premium to insure his structure against the earthquake. If you know the average annual loss cost, you know how much you are expected to pay every year. I mean, the earthquake might not occur every year, but you're expected to pay that cost averaging out for, let's say, for the next 50 years. And so if that is the cost, the insurance companies has a base now. The insurance company knows most probably this is the amount that I am expected to pay every year for next 50 years. And I'm going to charge the owner of the building, let's say, for example, more amount than the average annual loss. Why? Because the insurance company also has to cover its own expenses. They have staffs that they have to pay salaries for. Obviously, they need to have profit margins and stuff like that as well. So again, very good information for the insurance companies, but also good information for the owners as well. Because if the owner knows what my average annual loss is, the owner can again then negotiate with the insurance companies to lower down their premium, because they know that their structure actually has a lower average annual loss cost. So they should not be paying very, very high premiums for insurance to insure their structures against earthquakes. So let's say, for example, as Mr. Strong mentioned, recent earthquake in Myanmar, and also there were some damages in Thailand as well. Um, we are hearing stories that now the cost to insure your structure against an earthquake uh, is going to increase, right? So the insurance company might want to charge you more, and people might be afraid and might want to pay more money to insure their structure against earthquake, not necessarily to because their structure is going to collapse, but they need to repair that structure if earthquakes are occurring frequently. And so they want to insure their structure, but they don't really know whether the amount that they're paying to the insurance companies is actually, is it very expensive? Are the premiums too high or too low, or where are they? And when you run the resilience-based design procedure, you actually now know what kind of a cost you are expecting to pay. And you might also see how much the insurance company is charging you, and make your decisions whether you want to buy that insurance or not, or whether that insurance is good enough or not, or you may be better off just paying for the repairs by yourself also. So this is a very, very good information that the owners as well as the insurance companies can use as well to make informed financial decisions. Um, Another very important information that this is especially for the people who are looking to retrofit their buildings after the structures, is what we call the net present value. And so what is net present value? So net present value basically is the amount of money that you are going to pay, total money that you are going to pay for a future period, let's say 30 years, 50 years, for repairing your earthquake. So average annual loss was you are paying that thing average annually, but net present value actually is the total money that you are expected to pay next 50 to 30 years. But net present value does not only consider the repair and replacement costs. Net present value also considers the downtime cost. So if you have a structure which is generating you income, because your structure is going to close down, you're losing that income also. And net present value actually considers that cost as well. Now, net present value actually converts the future costs into today's money. So what do we mean by that? Well, let's say, for example, um, that you have a certain amount of money today, and you might want to look to invest that money and get some profit from somewhere. Let's say 5%, 10% profit, you might invest somewhere, you might get that profit. Now, if you are saving that money to pay in future, that money would be worth less, because if you invest it today, your money will return you something and you will have more money, obviously. So net present value actually converts the future cost to the cost of today, right? And it uses what we call the discount rate to do that conversion. And I have an example which we will see in the next slide as to how we are actually converting the cost that we are expected to pay in the future in today's money, and compare it and make decisions whether we want to repair our structure. So the slide that I'm showing you here actually is an example that I've taken from FEMA P58, and it's a very, very good example. So say, for example, that you have a structure and you ran uh, what we call the time-based performance assessment, and you got the average annual cost. And the average annual cost, let me just annotate on my screen. The average annual cost for that structure is 150,000 USD. So that is the amount of money that you are going to pay on an average every year to repair your structure against an earthquake. And the average repair time is 5 days. So usually you are losing 5 days of your business because of the earthquake were to occur. This was the initial time-based assessment. But let's say the owner has a certain amount of money that the owner wants to now invest into the structure to make it seismically more strong. The owner might have about, let's say, $3 million that the owner might want to invest. And what happens is that when you run this, when you strengthen your structure, because now your structure is stronger, you are expecting to have less earthquake damage, and you are expected to have less time that your structure will be will need to take upgrades, because the number of damages are low. And so after repairing the structure, now your average repair costs are about $50,000, and then your repair time is down from 5 to 3 days. So we are able to reduce annually, we are able to reduce $100,000 or $100,000 cost, because we are doing an upgrade. But the upgrade itself is costing us 3 million. So we want to know whether, when we do this, whether it's worth it or not. Also, the repair time is down. Now, if you look at it in simple terms, the cost that we are saving by doing the seismic upgrades is about 100,000 USD, right? So this is the cost that we are saving. But let's imagine that your structure also is generating you income, and the income that the structure is also generating is also 100,000 USD per day. Now, if you take the avoided costs are now 100,000 USD, because we were able to reduce our repair cost from 150,000 to 50,000. Every year we can now save 100,000 USD. Again, because the downtime cost is $100,000 per day, and we are able to save 2 days of repair time. So we have 2 extra days with which our business will operate, and then we will have income generated. So annually, now we are saving about 300,000 USD, 100,000 from the repair cost. And because our repair time is down from 5 to 2 days, we have an additional 200,000 from the income that we are going to generate. So in total, if we look at this, we are now able to save about $300,000 annually. But that $300,000 annually we are saving in future costs. Now, if we were to say how much money we will save in next 10 years, the simple answer would be 300,000 into 10, so about 3 million. But that 3 million is not in today's money. That's the money that you are expecting to pay in the future. But what is the worth of that 3 million in today's money? Because when you are doing the seismic upgrades, you are paying $3 million in today's money. Now, net present value actually uses this equation, and this equation actually is a very simple equation. It's an annual series equation where we are actually just taking the annual payments and then converting them into today's money, right? And so when we use the net present value equation for next 10 years, the 300,000 that we are saving every year, sum them up together for next 10 years in today's money would be worth only $2 million. So let's say, for example, now you are investing $3 million to save your cost, to lower down your earthquake expenditures, and you are thinking, well, next 10 years I'm going to be able to recover 300,000 3 million from my earthquake repairs. But actually, no. In today's money, that future 3 million that you are saving is actually worth only 2 million. Now, if you are intending to sell your structure after next 10 years, investing 3 million today is not a good decision, because in next 10 years, the amount that you are saving is only $2 million in today's money. Because that's the benefit of net present value. We bring everything to today's money, not the money worth in future. And again, if you want to keep it indefinitely, your structure for an indefinite period of time would save you about 4 million USD. So if you're keeping your structure for a long time, that 3 million upgrade is worth. Now, one thing that I forgot to mention is that the net present value uses what we call the discount rate. And discount rate actually here in this example is used as an rate of investment. So rate of investment basically is, let's say, for example, you have 3 million today, you want to invest that 3 million somewhere rather than upgrading your structure for earthquake, your money will be worth more. And that is the same amount by which we are actually now lowering down the future money to today's money. Now, this is a very simple example where we are doing this only based on the investment rate. But again, the future money actually is worth less, not only because you can invest your money today, but also you can because of the inflation and stuff, your future money will be worth less by definition anyway, right? So net present value, again, you can only use if you run time-based assessment, because you will need the annual average repair costs coming from the time-based assessment to calculate your net present values. And decisions, financial decisions about your structures, informed financial decisions about your structures can be made if you are running time-based resilience-based design assessment. And with this one, again, you can see that in this very simple example, if you are intending to keep our structure for next 10 years and then sell it off, the 3 million investment today is not worth it, because in next 10 years, you're expected to save only 2 million in today's money. But if you want to keep our structure indefinitely, then we should look to repair, because if you keep it for a very long time, eventually we will actually recover whatever we are investing today, right? So let me just close the annotation and then continue. Okay, so let me just, yeah, okay. So then just to conclude, so the time-based assessment actually now is a framework where we are not looking at a single intensity, but we are looking at multiple intensities, and then we can make decisions about the structures costs that are associated with the earthquake repairs. And we are not looking at a single event, but we are looking at multiple events. And we can use the quantities like average annual loss and net present values. And then these parameters can help us make sound financial decisions based on the information that is coming from our structure. You can see that the entire thing actually is based on the mathematical model that we created, and also the results that we got from that mathematical model. So we are not actually just randomly simulating or generating realizations, or what we call events. Those realizations actually get their information from whatever we provided to the procedure initially based on our results from the nonlinear model. So the framework as a whole now is empowering the owners as well as the people who have a stakehold in the structure to make informed decisions. Another way you can also think about this framework also is that, let's say, for example, you might also want to look at, when you are initially designing a structure, you might also want to look at different designs and then the earthquake repair cost associated with those designs. And you might want to compare whether your initial design has a certain cost, which is, let's say you're comparing two designs, one design is more costly than the other design, but maybe when you look at the resilience-based design procedure and compare the cost that will be associated with the repair time, your design that is cheaper right now might have more repair costs associated with it. So you might want to invest a bit of money today to avoid huge future costs as well. So the procedure itself actually is very good because it relies on the information provided by us from the nonlinear model itself, which is the information that we use to make the design decisions for performance-based design anyway.